Hey everyone, and welcome to the first video on what will be the final section of the inorganic chemistry part of Chemistry 2. And this is the D block elements and their chemistry. This is going to be a fairly big section, the biggest so far. It'll have 11 or 12 videos across 3 lectures. And the reason for this is that the D block chemistry and the metals themselves are so important, and the chemistry they do is so broad. So they'll find applications from catalysis to biological systems, drugs, and also pigments and things like colourings for paints. And because it's so broad, it's really, if you go into academic research in inorganic chemistry, using the D block elements and or compounds of those elements is really the biggest research group of inorganic chemistry. It really rivals organic chemistry and all the hydrocarbon research as like a size. I'll start then by highlighting what the D block is, what the elements are like, and then highlighting some of the broad applications I alluded to on the previous slide. So I've got a very small version of the D block up here. We'll see it a lot on the way through the lectures, but it's essentially that part of the periodic table that we've kind of been pretending doesn't exist up until this point. So it's sandwiched in between the S and the P blocks of the periodic table. It starts at period 4 and carries on down from there, and it encompasses groups 3 to 12 of the periodic table. Now it's nowhere near, or the elements and their states of matter are nowhere near as diverse as the P block. So for all of these, they are all metals, also referred to as the transition metals, because they transition from the electropositive metals of the S block to the more electronegative elements in the P block. And with the exception of mercury in the bottom right here, they're all solids. Mercury's one of only 2 of the elements that's liquid at room temperature. They follow some of the general trends that we've already seen through the periodic table. So if we go left to right or like across a period, the electronegativity increases, and as we go down a group, they become less electronegative. And now I highlighted some of the uses in the previous slide as well. So 9 of the elements are essential to life. So these will be in things like vitamins and hemoglobin in your blood contains iron. And this link here is to the Encyclopedia Britannica, which highlights the biological functions of some of these transition metals. They're also used as catalysts. So we saw a lot in the hydrogen lecture how the Haber-Bosch process feeds most or half of the world's population through the plants it can fertilize, and the Haber-Bosch process is only possible by using an iron-based catalyst. Another example is vanadium. We saw in the P block lectures about sulfuric acid, and that's made through the contact process. SO2 going to SO3, that uses a vanadium catalyst. And they're also used in pigments, which I've got examples of down here, and medicines. Now the pigments use comes from the fact that the complexes of these elements, which we'll talk at in a later video of this lecture, their complexes are really brightly coloured, and they can be tuned to many different colours by putting different bits on them. And we'll look at this in a lot more detail. We'll talk about complexes at the end of this lecture, and then the final lecture will actually talk about the spectroscopic side of things and how the colours change and how we can measure those in a lab. Now, one thing to note with the D block is that group 12, the last one on the end here with zinc, cadmium and mercury, this doesn't fit the term transition metals, because the IUPAC definition of a transition metal is just one that has an atom with a partially filled d orbital. However, group 12 has a completely filled d orbital, even as ions in compounds. And therefore, group 12 are just referred to as D block metals and not transition metals like the rest of them. So here's some example of the compounds that can be used and researched. So this is one of the most sensationalized pieces of journalism you'll ever read. You can see from the URL and the title, alien metal that wiped out the dinosaurs could cure cancer. So basically it's one of these iridium complexes, and as I said, we'll talk about complexes later, but it's a drug that can use iridium to selectively kill tumour cells and cancer cells when irradiated with light. But yeah, they sensationalise it so much in this article. So iridium first came to Earth on the asteroid that wiped out the dinosaurs, apparently. So it's referred to as an alien metal that came to Earth 1 million years ago. And this part, so what this complex does, if you shine light on the iridium, it can change the state of oxygen from having 2 unpaired electrons to a pair of electrons. And this is called going from ground state oxygen to singlet oxygen. And singlet oxygen is a real powerful oxidizing agent, and it can kill tumour cells. And it's really important. So obviously they didn't settle with that explanation. They said that by blasting it with a laser beam, you can create poisonous oxygen, which I suppose is accurate, but quite sensationalized. And here are some other examples of complexes that have found use in real life, popular life, I guess. So a couple of platinum complexes. There's this one with 2 chlorines and 2 ammonia on it. This is called Cisplatin. It's used to treat testicular cancer. A similar one, but with a different ligand, we call it, and we'll go into this in much greater detail in the 4th video. It's called carboplatin, and this treats a wide range of cancers. And then vitamin B12 actually contains cobalt with a very large ligand around it. Now let's start having a closer look at the D block and some of its properties, and start looking at how some of the chemistry is dictated by its D valence electrons. So I've got the D block from the textbook here, and you'll see it's a bit different to the one I showed on the first slide. So I'll highlight those first. So first off, we've got this purple bit here, which is highlighting that we've removed the F block elements, much in the same way I used to do in the first few lectures of this course, with having the S and the P block with the D block taken out. We show the D block with the F block taken out. And you'll see on all the periodic tables, these are the 2 rows that are right at the bottom of the periodic table. But this is where they'd fit in. But we don't include them because, where their valence electrons are in the F shell, they behave very differently to the D block. Also, we have period 7 on this one, which I didn't show in the previous D block. And this is the 4th row. And this is because the heaviest members, at the bottom of each group, these are synthetic elements. They usually don't last very long. Like, they can exist for less than a millisecond and then break up sometimes. And they're synthetic ones. So there's quite a few research groups like creating new elements, trying to find new elements that are actually stable. I think they do this mainly by just bashing nuclei together at incredible energetic conditions. And because of that, they're quite unstable. So this is added, but we won't be looking at it. It's really the first 3 periods that matter, and these are referred to as triads. So like this one's highlighted here, iron, ruthenium, osmium, and they're known as a triad. And usually they've got similar behaviour to each other. So for example, for my PhD, I was working with catalysts that do the reverse of the Haber-Bosch process, so breaking down ammonia back into hydrogen and nitrogen. We were hoping to use ammonia as a fuel, so it's a source of hydrogen. And iron's a very good catalyst for this, much is like it is for the forward reaction, the Haber-Bosch process. Ruthenium is an even better catalyst for this actually. And osmium is also very active, but it's super rare and super expensive, so no one actually researches it. So you can see they do have trends in these triads. The other popular one is the copper, silver, gold triad. And these are also called the coinage metals because they're used in coins. Sorry, I had a cough. Of the D block elements that are mainly found in the Earth's crust, or the most abundant ones, they're in the 1st row. So iron is the most abundant one in the Earth's crust, but you can find a lot of titanium and a lot of these in the Earth's crust, but not so many as we go down. Now the chemistry of D block elements is dominated by forming cations and losing and using electrons from their valence D orbital. So to understand this, we really need to understand what's going on with these D electrons and where they exist. So we'll go back and recap the Aufbau principle and then kind of correct a few white lies that I told, and you've probably been told up to this point, to make it more accurate to help with the D block. So first off, the Aufbau principle we saw in the very first video was that when we're putting electrons in an orbital, we build up from the lowest energy to the highest. So we go 1s, 2s, 2p, 3s. But then we actually see that the 4s is supposedly lower in energy than the 3d. So we fill the 4s orbital before the 3d. Now in the D block that I've got highlighted here, let's look at the first row, because we can actually see there are some exceptions to this rule. So if we look at chromium here and copper, we can see it hasn't actually fully filled the 4s orbital before filling the 3d. They've both got a 4s1 and then either 3d5 or 3d10. And the reason for this is that half-filled orbitals and fully filled orbitals are much more stable. So it's actually more energetically favourable in the case of chromium and copper. Instead of pairing two electrons in the 4s orbital, to have those unpaired and then create a half-filled or fully filled d orbital instead. Now, as well as highlighting some of the anomalies to this rule, I should actually clean up something that is pretty much an outright lie. We've said until now that the reason the 4s orbital is filled before the 3d is that it's because it's lower in energy. But we can see in this graphic I've got here that this red line that highlights the energy of the 3d orbital and the blue line highlights the energy of the 4s orbital, that when we enter the transition metals and go across them, the 3d orbital is actually lower in energy than the 4s orbital. That doesn't change anything though, because the 4s orbital is still filled first, as we saw on the last slide, with a couple of exceptions. The reason for both of these things, so firstly, the reason that 3d becomes lower energy than 4s is because the attraction and repulsion energies change as we're adding protons and electrons. However, just because the 3d is lower in energy, the electrons prefer to first go in the 4s orbital because it's more diffuse, is written here, and it's in the textbook as well. What more diffuse means is just larger and spread across a larger area. So it minimizes the electron-electron repulsions by the pair of electrons in the 4s orbital. Still, it's good to know that with the exception of chromium and copper, like I said, filling electrons using the Aufbau principle still works. It's just not the theoretical reasoning behind it. Now, if it works, even though it's not the theoretical reasoning behind it, you're probably wondering, why have you confused me with all this these lines about the energy levels of various orbitals? Why can't we just pretend that the 4s is lower in energy than 3d? Now, this really matters for the transition metals because, as I was saying, they form cations and their chemistry is dominated by it. And if they form cations, it means they're losing electrons, and we need to know where they're losing those electrons from. So when we make compounds of, just cations, we won't even go into the compounds just yet. If we're making cations, we see that the 4s electrons are lost first. Now, if the 4s was lower in energy than the 3d, we'd expect that when we're making cations, we'd remove them from the 3d orbital first, kind of a last in, first out principle. But in actual fact, it's first in, first out. So we build up, putting the electrons in the 4s first. Then when we're making cations and ionizing them, we actually take them from the 4s first also. But why is this even important? Like, why do we actually need to know that they come out of the 4s orbital first rather than the 3d? So it's important because, as I was saying, the transition metals and their compounds, or complexes as we'll come to know them, are made with cations, and we need to know the electronic structure of these cations because this really dictates the shape of these compounds and a lot of the properties of the compounds. And one of the important things is that in a transition metal compound, the electron-electron repulsions are lower. So these 4s electrons, if there's space, are actually put in the 3d orbital. So let's take an example here, scandium, let's say. This is a nice and simple one, the very first transition metal. So its electronic configuration, as a metal, just as an element as well, is 3d1, 4s2. Then when we make a compound out of it, even before it becomes a cation, sort of just, a thought experiment of scandium with all its electrons but in a compound, this lowers the electron-electron repulsions and makes the 3D orbital, more attractive. So it's already lower in energy than the 4s, but the electron-electron repulsions are lowered. So it's just happy to be in the 3D. So scandium in a complex, in our theoretical compound, will have the electronic structure 3d3. Now, if you want an example of how to calculate the electronic structure in compounds, I've highlighted this one here, which is pretty helpful, the worked example on page 1259. I worked example 28.1, the box at the top of the page. But it's also got a question at the end of it, which is work out the electronic configurations of cobalt 2+ and cobalt plus. Now it's here that this piece of knowledge becomes really important. So let's look at cobalt's just normal metallic structure. So cobalt has 3d7 and 4s2. Now it's really important because we're looking at small cations here, like 1+ and 2+. If you get to things like 3+, it's super easy because we can just take them out of the 4s first and then take them out of the 3d. But you'll see here why it's important to know that they go in the 3d orbital in a compound. So if we look at cobalt 2+ first, to work out the electronic configuration, we put the 4s electrons in the 3d orbital, so this makes it 3d9, and then we take these 2 electrons to make it 2+, so take 2, and we end up with 3d7. So that's the electronic structure of cobalt 2+. And as I said, we could have just done that knowing that they leave the 4s orbital first. We just take the 2 out of here and we're left with 3d7 also. But it's when it comes to questions such as this with cobalt 1+ that we really need to know that in a compound these 4s electrons will go in the 3d orbital. So if we pretend we're not doing it properly, we could say that the electronic configuration will be 3d7 4s1, just by that old thinking of taking electrons from the 4s orbital first. However, this is completely wrong. If we actually do it how we did for the last one, so we put all the 4s electrons in the d orbitals because there's space for them, and then take away our electron, we end up getting 3d9 at first, and then this time we're taking 1 electron because it's 1+, and then this actually results in the electronic structure of 3d8. And this is what the electronic structure of a cobalt 1+ cation would be. So it's not 3d7 4s1. It doesn't just come from the 4s orbital. The 4s electrons go into the 3d orbital because it's more stable in a compound, and then they're removed from there. So that's really important to know. And as I said, go through that worked example, and hopefully that will make it a bit clearer as well.